In this video, I will talk about 4 different sample confidence intervals. All right, the first one. Well, I will write down the 4 first. The first one is 100 times 1 minus alpha CI for population mean. When population variance is known. The second one I shall talk about is 100 times 1 minus alpha percent confidence interval for population mean when population variance is not known. Right, and the third one I shall talk about is 100 times 1 minus alpha percent confidence interval for population variance. Okay. And the fourth one is 100 times 1 minus alpha percent CI for population proportion. So these are the 4 confidence intervals I will derive in this video. And so for each I will give you a derivation, in other words the proof. And you will need to know the proofs for each of these confidence intervals as part of this course. Okay, so let's start with the first one. So number 1 is so I will show you how to derive this, in other words, the proof of this. Right? So I'm going to suppose that you have a random sample x1 to xn, which are IID, normally distributed with mean, mu, and variance sigma square, with unknown mu and known sigma square. Remember, sigma square represents the variance, so we are assuming that the variance is known. Now you may recall from the video that we did on normal distribution, one of the properties I gave you in that video is the following, that is that the sample mean, if you have a random sample from this, then the sample mean also has a normal distribution with these parameters. If you want to see, okay, so I see video on normal. This is a property I gave you in that video. All right. So if you don't remember, it, please see that. Okay. So this implies that x bar minus mu must have a normal distribution with 0 mean and variance sigma squared by n. And this implies that there's a normal distribution with 0 mean and variance 1, so which is the standard normal distribution. Now, you may recall from one of the videos I did, I think the video on percentiles I did not long ago, that if this has a standard normal, then the probability that so if you look back at the video that I did on percentiles, let me try to revisit it, explain. If you don't remember what I did in that video, suppose this is the PDF of standard normal, all right? Then there are 2 points. You can take 2 points along the horizontal axis, and this point will be, and this point will be here, and the area between them, that's this area here, is 1 minus alpha. That's because this point here has an area of 1 minus alpha by 2 to the left, and this area here corresponds to an area of alpha by 2, and this area here has an area of alpha by 2. So this point has an area of 1 minus alpha by 2 to the left, and this point has an area of alpha by 2 to the left. This is what I explained. I mean, if you look back on the video on percentiles, you will see. So the area between these 2 points, this point and this point, must be 1 minus alpha. That's what I'm saying here. Okay. All right. Now I'm going to convert this statement into a statement on mu, the population mu. So let me do that now. Then, okay, now you can convert this into the following statement. This is a statement on mu. Okay. All right. In the next step, I'm going to use something I mentioned in the video on percentiles. You may recall that these 2 points here are are mirrors of each other. So this is equal to this in magnitude because of the fact that this is 0. So they're symmetric, right? So Z alpha by 2, right, is equal to minus of Z 1 minus alpha by 2. So this is what I'm going to use in the next step. So I'm going to replace this guy here, right, by this. Okay. So what you get is the probability that x bar minus So I'm using this fact to replace this by this, right? So according to the definition I gave you in the previous video, we have a confidence interval for mu. So the conclusion is the following. So hence, okay, so this is the first of the four confidence intervals. Okay, I'm going to do the next one. Number 2 is the 100 times So here I'm going to suppose you have a random sample x1 to xn, which are IID, normally distributed with mean mu and variance sigma square, with unknown mu and unknown sigma square. All right. So, okay. The first thing you must realize is that you have a random sample from this, just like I did in the previous case. The sample mean must have a normal distribution with these parameters. So this is from the video on C, video on normal. It's one of the properties of normal I mentioned. Okay. Okay. Now this implies that x bar minus mu must be normally distributed with 0 mean and variance sigma squared by m. Okay. And this implies, you should look at the video on if you look at the video on T distribution, this is one of the properties I mentioned. So this is from the video on students T. Students T distribution. So this is one of the properties in that video, in this video. Right. Where S here, S is the sample standard deviation with n minus 1, not n, okay? Alright. Now the fact that this has a T distribution, remember T is also a symmetric distribution, implies that the probability that this must be 1 minus alpha, right? I mean, the reason for this is the same as in the previous case, right? So if you look at the percentiles video, you will make sense of this statement. I mean, in other words, let me try to draw the picture if I can. But if this is, it looks, the students D PDF is more or less like the normal PDF, right? So this is 0. This is the PDF of T n minus 1. Now you should take 2 points, say this one and this one, and if this is T n minus 1 minus alpha by 2, and if this is T n minus 1 alpha by 2, right? Okay. So this point here must have an area of 1 minus alpha by 2 to the left, and this has an area of alpha by 2 to the left. So this area is alpha by 2. This area, the area in between the 2 points, must be 1 minus alpha. And this area must be also alpha by 2. Okay, so you see from this picture that the area between these 2 points, this one and this one, must be 1 minus alpha. So that's why I made this statement here. Okay, I explained this in the percentiles video. So if you look back, you will see. All right. Now, from this statement, you can see that the probability that right? Okay, this follows from this, right? And next, I'm going to rewrite this as a statement on mu, right? So let me do that over here. So this is going to be, as a statement on mu, this will be the probability that x bar minus s over root of n T n minus 1 this is what you get. Now, in the next step, I'm going to use the symmetry. You may recall anyway, you can see from here that because of the symmetry of the PDF, these 2 points must be equal in magnitude, right? So I'm going to use that fact in the next video. That is the fact that T is equal to minus of T right. So this is due to the symmetry of this PDF of the T distribution, right? So using this, you can write this statement as follows. Okay. All right. Now, from the definition of confidence interval I gave you in the previous video, we can see that we have a confidence interval for mean. So the conclusion is the following: that hence 100 times 1 minus alpha percent CI for mu is the following. So the lower limit is simply this one, which is x bar minus s over root of n and the upper limit is this one. Okay. So this completes the second case where the population variance is unknown and we want to find the confidence interval for the population mean. Alright, the next, number 3, is we want to find 100 times percent CI for population variance. Right, so I'm going to suppose here that x1 to xn or IID normally distributed with these parameters, with both mu is the population mean, sigma squared is the population variance unknown. Alright, now in this case I'm going to use a result from the video on chi-square distribution. You may recall that if you look at that video, one of the results I mentioned is the following. Okay, this is, so if you look at the video on chi-squared distribution, you will see this result as one of the properties I mentioned. Okay. Alright, so this implies that the probability that right? So these two, once again, are percentiles of the chi-square distribution. I mean, I talked about them during the video on chi-square, during the video on percentiles. You may recall. You may recall the following picture. I don't know whether if you have seen the video, you will see that the PDF of a chi-square PDF is kind of skewed. So this is the PDF of this, right? And these 2 points here are the percentiles corresponding to area of alpha by 2 this end, and an area of alpha by 2 on this end, right? So basically this is your chi squared n minus 1 minus alpha by 2, and this is the chi squared n minus 1 alpha by 2, right? So because of the way they are chosen, the area between these two must be 1 minus alpha. That's what I have said here, that the area between these two must be 1 minus alpha, and the area over here must be alpha by 2, and the area over here must be alpha by 2. Okay. All right. Okay. So from this statement, you can rewrite this as a statement on sigma squared. So you will get the following. Now, because this is a skewed density, these are not equal. I mean, it's no longer symmetric, so you cannot say that this is equal to this. Right? So that means you cannot simplify this statement further, right? So the conclusion here is that hence so the 100 times 1 minus alpha % confidence interval for sigma squared is this to this. So the lower limit is this is the lower limit. And the upper limit is this. Alright, so this completes case 3. And the next case, which is the final case I'm going to look at, is a confidence interval for population proportion. So number 4, 100 times 1 minus alpha % CI for population proportion. Okay. So here I'm going to suppose you have a random sample x1 to xn, which are IID from a Bernoulli distribution with parameter p. P represents the population proportion. So P representing the population proportion is unknown. Right, I mean usually I'm sure you guys know about the Bernoulli distribution. Bernoulli is either takes the value 1 or 0. 1 with probability p, 0 with probability 1 minus p. So if, for example, to describe things like whether you smoke or not, whether you pass or fail, whether you are male or female, and so on, things like that. So P could denote, for example, the proportion of smokers or proportion of people who passed, and so on. Okay. Okay. Now, if you must have done this in probability 1. The population mean mu, which is the expectation of xi, is the expectation of a Bernoulli random variable, which is p. I'm sure you know this. And sigma squared is the population variance, which is the variance of xi, which is the variance of a Bernoulli, is p times 1 minus p. Now the reason I have written these down is it's difficult to find a confidence interval that is exact. So I'm going to find a confidence interval that is an approximate one. And for that I'm going to use the result that we talked about earlier, which is known as the central limit theorem. I mean, I did a video on this earlier, you may look at it. So by the central limit theorem says that x bar is the sample mean minus mu, which is p, divided by sigma. Sigma is the square root of this, divided by n. It approaches the standard normal distribution as n approaches infinity. Right, but n, the sample size can never be equal to infinity, right? So you choose n large enough. People in statistics, usually we assume that anything greater than 25 is large enough, right? So that you can approximate this by this, right? So suppose so this is the notation for an approximation. I think I mentioned that before, right? Okay. Now, from this approximation, we can construct a confidence interval for P, right? So that's what I'm going to do now. So this implies that the probability that approximately equal to 1/1. Alright, the reason for this is the same as the reason I gave you for case number 1 of this video. Alright, now this is equivalent to saying that approximately equal to 1/1 alpha. Alright, and I'm going to continue this on a new page. Now, as a statement on P, we can write this as follows. Right. Okay. In the next step, I'm going to use the fact that these two are the same. I mean, they have the same magnitude, which I explained once again on the case number 1 of this video. So using the fact that z alpha by 2 is equal to minus of z 1 minus alpha by 2. That's because of the symmetry of the standard normal distribution. So using this, we can write the above statement as follows. Okay. Now, finally, because P is an unknown quantity, we cannot have an unknown quantity in the confidence interval. So, in the final step, I'm gonna approximate P by x bar. X bar is the sample proportion. This you can do because of the strong law of large numbers. Remember, the strong law of large numbers says that the population, where the population mean, P is the population mean for the Bernoulli random variable, approaches the sample mean as n goes to infinity. So that's what I'm using here. This is the strong, I'm sure you've done this before, strong law. If you don't know this, just remember that's what it says. The strong law of large numbers. And it says that as n approaches infinity, the population mean approaches the sample mean. So this is the population mean for the Bernoulli random variable, and this is the sample mean. Okay. So the final step, I'm going to replace these two p's and these two by x bar. conclusion is the following, that hence the conclusion is hence an approximate is the following. So the lower limit is this one, right, and the upper limit is this one. Alright, so we have done all 4 cases, and in all 4 cases I have shown you how to derive the confidence interval. So this completes this video, and in the next video I will do some examples on one sample confidence intervals.